Okay, so we will move on to the next presentation by Vasilis Zalokostas and Doris Kouvinis about the experiences from deploying the AETHER framework.
Hello, fellow students. My research interests focus on beyond 5G and 6G reconfiguration and management. Bill?
Hello, everyone from me. I'm Vasilios Zalokostas, and I'm doing a PhD just like Theodoris. We are doing a joint PhD with the Sorbonne University and University of Thessaly, and my interests are around virtual network functions and its integration with machine learning for 5G networks and beyond. Let's dive into the presentation. Not working. So during our stay in Sorbonne, we experimented with AETHER framework. AETHER is the first open source 5G connected edge platform for enabling digital enterprise transformation. It provides mobile connectivity and edge cloud services for distributed networks, and it can be operated through a cloud managed offering using cloud-based technologies, just like Kubernetes. It is optimized for multi-cloud deployments, and it provides simultaneous support for wireless connectivity over licensed, slightly licensed, and unlicensed spectrums, or CBRS. Generally, AETHER represents a complete solution by democratizing the availability of a robust and complete software-defined 4G or 5G networks to the developers. Also, it is built upon a number of world-class components, just like SD-RAN or SD-Core. So why AETHER? Because AETHER brings together private secular 5G technologies alongside with edge computing, and it's delivered as a cloud managed platform with three main services. The first one is the connectivity service. As I told you before, AETHER provides 5G performance, reliability, and security that is very important for critical mission apps that require low latency, predictive performance, and maximum security. Also, it leverages between the CBRS spectrum, and it's very easy to deploy, just like the Wi-Fi. In addition to connectivity, AETHER provides edge computing too, and it's optimized for multi-edge sites. It supports ML-driven IoT and OT operations, and it gives developers many opportunities and options by the modernization of the deployments with data aggregation, data compression, filtering, and analytics to reduce the bandwidth. Finally, AETHER provides end-to-end slicing, which is basically slicing between the radio access network and the mobile core. AETHER is built in a way that for every enterprise that is using it, the developers can specify the flows and the resources needed, and their priorities. Also, the resources can be provisioned for a deterministic latency and availability. Having these services, we get a lot of very important attributes. The first one is quality of service, which, as you can see in the picture, comes with three levels. The first one is per device per application, which is basically the flows between the device and the application. An application can have many kinds of flows, but it is possible to specify a few of them. The second one is the per device, which is basically all the flows which consists of the flows of all applications in a device. And lastly, is per slice, which is all the flows of all applications of all device in a particular slice. Also, security is being guaranteed as the 3GPP SIM-based encryption and authentication is being applied. Ether is also programmable and customizable to the needs of any enterprise that utilizes. Another important feature is the fine-grained visibility, which allows us to monitor every packet transmitted. With that power in our hand, we can optimize the resources to our needs, such as CPU, memory, and radio resources. Last but not least is the verifiability, which basically means that we can verify every packet transmitted, if it is forwarded or not, by the intent of the enterprise or the application. Regarding the availability, there are two options for deploying Ether. The first one is Ether in a box on hardware radios, which is the one that we followed. It basically describes how to set up Ether with Node B and connect real devices for experimenting purposes. As far as the equipment needed, we needed a server for running the Ether in a box tutorial with respect to SD core, UPF, and ROG. We also needed an 4G, 5G Node B, just like the Circumcell CBRS LTE. And we also needed some SIM cards and TED devices in order to test our deployments. The other option is Ether in a box for developers, which is basically describes how to deploy SD core and ROG. And it also needs a server for the Ether in a box to run, and OAI SIM is also needed. We also added 2 QR codes if you want to check the tutorials yourself and explore it. Now, Thodoris will take the floor to say some things about the Ether architecture and the setup that we implemented.
Okay, so this is Ether's architecture. Ether can be seen as an open source private 4G, 5G edge cloud as a service network. As we can see, it has two entities, the Ether connected edge and the Ether central. What it requires is the deployment of a few small cells that they can operate over CBRS and a connected edge in which the user plane core network functions running as providing a low latency. The connected edge runs on the SDN substrate in which the owner's controller running, providing and applying a quality of service to the users and applications. Specifically, Ether supports 3-level quality of service metering, as Vasilios mentioned before. One is per device, per application. The other is per device and per slice. The Ether management platform, as well as the Ether connectivity control, running the cloud along with central IoT and AI/ML applications. And also it's important to mention that the Ether Central control and supports all the connected edges. So our setup is partly located at the Sorbonne University at one lab for the edge infrastructure of the previous architectures that we saw before. And the University of Thessaly at the NITOS testbed for the Ether connectivity control and the cloud. To deploy the Ether framework, we utilize some cloud-native tools like OpenStack to create some virtual machines. As with OpenStack, we can scale the virtual instances and have portable configurations across the servers. And we also use Kubernetes to deploy the core network functions as microservices. As you know, with Kubernetes, we can rapidly deploy clusters, manage network functions, and that are running in containers, and scale out capacity to meet the big demands. It's also important to mention the hardware that we used. We used 2 CBRS LT Sercom cells for the Ether in a box of hardware radios. And also, okay, these cells are, as you can see, the right, down right, are connected directly to the servers. And there's another one option, as mentioned before, the Ether in a box for developers, in which you can run the open-air simulation to evaluate the developer commits. We also used one cell phone that supports the CBRS frequencies, which in our case was an iPhone 11 for connectivity tests. So this is our setups architecture. A random user plane core is running at the edge at the Sorbonne University, and the control plane is running at the University of Thessaly at the NIDOS testbed for the Ether connectivity management. The communication between them is based on a layer 3 connectivity VPN link. The latency is still low because the user plane functions of the core network are deployed in the edge side. Okay, so let's now move on to the demo. So we are in a Kubernetes environment, and with a kube control command, we inspect all the deployed pods of the SD core network, which are deployed on the OMEC namespace. We see that all of the OMEC components are running successfully. Then we see all the necessary pods that are running for the deployment of the Ether framework, such as the kube system pods, as well as the pod networking pods, which in our case, the pod network is Calico. We also see some pods for the SDN controller, which is the honest controller, which is responsible for the user plane and quality of service. And finally, we see some pods running that are responsible for the user interface, such as the ROC graphical user interface, and for monitoring, such as Prometheus and Grafana. Right now, we'll go into the Grafana dashboard to monitor the health, as we see, of the inode B, to see the status of the inode B, as well as to see the subscribers that are connected to the network. We also can see the traffic through the time and the U activation over time, and the current throughput between the UE and the UBF. As you can see, our phone is successfully subscribed with this IMSI, and now we'll try to switch on the LTE on the iPhone to connect to the network. We immediately see that the TX bitrate on the UBF metrics increased as soon as we're connected to the network. And now we'll start to try some ping to test the connectivity to the core, and we see that the packets come and go successfully with some quite good latency values, despite the fact that the control plane of the core network is running at the NIDOS testbed. And then we will explore a little bit more the the ROC user interface, which uses the opportunity to create some slices, create a new slice or edit the current one by changing the policies. For example, right here, we have one slice for this one UE, which has a default behavior to allow all the traffic. And there we can change the maximum bit rate that experiences. Of course, we can have multiple slices per UE. You can also, as you can see, configure and add or delete the subscribers with an easy way. It's a very easy way to do it. And finally, we can also see the inode bees or configure the inode bees or gnode bees to the network. And also we can configure the IP domain on the fly. Finally, we can monitor the consumption of the core network functions in terms of memory, bandwidth, or CPU. For example, here we are on Grafana dashboards, so we can see all the received transmitted bandwidth of the OMEC pods. In another dashboard, we can see and test and monitor some other metrics. For example, here we monitor the CPU usage of the AETHER deployment. Or we can go to another dashboard to monitor the core network functions, memory usage, or CPU usage, one by one, as you can see here for MME, for UPF, etc. Okay, so our future step is to experiment with SD-RAN, which by the time is not compatible to AETHER for hardware devices. It's compatible only with OpenAir interface CU/DU and RAN simulators. The SD-RAN incorporates the O-RAN architecture as it exposes all the necessary interfaces like A2 or O1, A1, and the protocols, the corresponding protocols such as ASN1, STP, netconf, etc. Also, it uses its own recontroller, the ONOS controller, which is suitable for the high availability and performance and can be integrated with third-party XApp vendors. In this way, we can experiment with the O-RAN architectures and its fertile ground for the development of various AI, ML X applications. To summarize, AETHER is a very good solution for private 4G and 5G networks, as it provides quality of service and security. It also enables federated and distributed experimentation, which meets the objectives of the SLIDES project. And finally, it's open and it's open source and programmable, that's very good for researchers and academia. So this was it. We'll be more than happy to answer all your questions. Thank you.
Well, are there any questions from the room? I do not see any questions. Oh, no. So there is a question online. When we compare the AETHER architecture to the ORAN and the MEC framework, it seems like AETHER can provide more or less all the services provided by MEC and ORAN. Is merging these two architectures was one of AETHER design goals? So the question is that AETHER, when we compare the AETHER architecture to ORAN and the MEC framework, it seems like AETHER can provide more or less all the services provided by MEC and ORAN. is merging these two architectures one of the AETHER design goals?
That maybe this.
Yes,
answer
Rafael
this.
is
Yeah,
typing an answer, I see. So what Rafael is saying is that it's not necessarily it was designed having in mind ETIMEC, but there were many other synergies like with its development. Okay. If there are no other questions, then we're a bit ahead of the schedule. We're going to have a lunch break, and we will resume at 2:30 local time. Thank you.